Recording in progress.
Is also online. Am I audible? And am I visible? Can someone respond?
Yes, sir.
Yes, sir.
What was the last topic which was there?
Renard observation.
Sorry. Hallwards and Renault Express, right?
Yes, sir.
We'll start from there itself. Because as I told you, I have not got the main context of this chapter. Right. Now I hope my screen is visible. Right. So before I get started, I just want to recollect few concepts that we discussed yesterday. The points that we were concentrating upon yesterday were the first term that we saw is what are free electrons. So free electrons are confined to the metals, means those electrons which can actually participate in the conduction is what we call them as free electrons, right? So for you to remove an electron from a metal surface, we need to supply some energy. That energy can either be in the form of heat, light, or it can be in the form of secondary emission, or it can be in the form of electric field. Right? So depending on what kind of energy we are supplying, the emissions are classified into different types. Suppose you supply heat. Because matter itself has a magnetic field. Okay. So that's why we use only electric fields. Okay. The question is, if suppose you are supplying temperature, you are supplying heat, and the electron is getting emitted, that kind of an emission we call it as thermionic emission. And the electrons that are coming out are called as thermoelectrons, or you call them as thermions. In a similar way, when you supply field and remove the electrons, you call them as field electrons, or you call the emission as field emission, right? And similarly, if you supply light and make the electrons get liberated out, then you call that as photoelectric emission. And in this chapter, our main context is going to be about photoelectric emission. And the last one is, if you use another electron, a fast-moving electron, try to bombard it with the electron and knock the electron out, you call that as secondary emission. Secondary emission is you already have an atom, there is a valence electron. So on this valence electron, if I use another fast-moving electron to hit and this electron gets knocked out, we call that as secondary emission. Right? So having said this, then we got into the concept of what is photoelectric effect. So photoelectric effect basically means in a particular material, if you are able to remove an electron with the supply of light of sufficient frequency, this is very, very important. So for you to remove an electron from a metal surface, you need to ensure that the energy being supplied is slightly greater than the energy which the electron already possesses. And that minimum energy is what we call it as work function. Right? You would have heard about threshold energy. So threshold energy is something like work function. right? So you can call it as another name also, right? So work function is the minimum energy that is required for the electron to get liberated from the metal surface. Okay. And then we got into the history of how this photoelectric effect actually started. First, it started with Heinrich Hertz, right, in the year 1887. So what he did is when he was trying to prove the presence of electromagnetic radiations, right, accidentally he observed this phenomenon. Later, there were two scientists who took over the observation and started creating an experimental setup to explain the process. And that is what we are going to start with today. And the name of that observation is Hallwatch and Leonard's observation. So they are the two scientists who are working on Hertz observation. Okay. So during the year 1886 to 1902, William Hallwatch and Philip Leonard investigated the phenomenon of photoelectric emission in detail. Okay. So what they did is they took a zinc plate. So Hallwatch, what he did is he connected a zinc plate to an electroscope. Electroscope is basically a device which is used to check the presence of charge. Okay. So on the zinc plate, what was happening is he observed that when the zinc plate was illuminated with ultraviolet radiations, that is UV radiations, there were three important observations that came into consideration. First thing is, if the zinc plate was initially negatively charged, it became uncharged, means it became neutral. Why? Because electrons were getting released. In a similar way, if it was already positively charged, okay, I'm reading the third point. If it was already positively charged, it became more positively charged because electrons were getting liberated, right? And if the plate was initially uncharged, then it got positively charged because electrons are getting liberated. So all the three contexts tells us that electrons are being released, right? So having said this, so those electrons are called as the photoelectrons, right? All these points I've already discussed. Now, from these observations, what is the important conclusion that we can draw? So we can conclude that some negatively charged particles were emitted by the zinc plate when it got exposed to the ultraviolet light, and those, okay, when they got exposed to the ultraviolet light. Now the question is, what happens if this ultraviolet radiations were stopped? So when it stopped, the photoelectrons getting emitted also stopped. So it was an instantaneous process. Means you could observe the photoelectrons coming out only as long as the ultraviolet radiation was falling on the metal surface. So have this point in your mind. Okay, this is a very, very important point. Based on this, we are going to discuss certain graphical analysis in the future. So have this point in your mind. As soon as the radiations falling on the plate is going to get stopped, current will also stop. Okay. Now, from these observations, again, we can indicate that ultraviolet radiations incident on the emitter plate C eject out same negatively charged particles from it, and those negatively charged particles were called as see a diagram. Okay. So what I do is, this part is going to get repeated again. So I directly step into the next concept. So I'll step into the next concept that will give us a clear-cut explanation of what is the plate C and plate A. Okay. So the combination of all these Hallwatch and Leonard's experiment put together gave us an experimental study of photoelectric effect. Okay. So in this experimental setup, what we are going to do is, we will see how the setup was firstly done. So you have a tube, okay? You have a glass tube which is evacuated. Evacuated in the sense, it is vacuum. There are no air particles present in it. So in this evacuated chamber, there are two plates that are connected. One is plate C and the other is plate A. And C you can call it as cathode and A you can call it as anode. Or you can say C is the emitter plate and A is the collector plate. Why is it so? I'll explain it. Okay, I come again. So in this evacuated glass chamber, there are two plates. What are they? C and A. And this C and A are connected in turn to two other devices. One is a microammeter and the second is a voltmeter. So that is to mainly measure what is the potential difference existing between the collector plate and the emitter plate. And microammeter will show you the amount of current that is flowing through the circuit. That current is called as the photo current, right? And most importantly, the collector and the emitter and the collector plate are connected to a high tension battery. So HTB stands for a high tension battery, which is in turn controlled with the help of a key, and it is connected across a potential divider. So that you will be able to control the amount of potential you are actually trying to supply to the plates. Okay. So having this setup in mind, okay, I repeated, having this setup in mind, let's try to do a study of how this photoelectric effect actually takes place. So it's very, very simple. Okay. Now listen to this. Suppose on this evacuated glass chamber at a particular point, I have a quartz window. So what does this quartz window do is, whenever you have a source of light, that source of light will be made to fall on the emitter plate. That is a cathode. Right? Why I call it as cathode is because it is the one which is connected to the negative terminal plate. And A is the collector plate is generally connected to the positive terminal of the high tension battery. Okay. Now listen to the logic that I'm going to tell you. Okay. So first we need to understand this experimental study to describe certain changes that are occurring in the parameters with respect to photoelectric effect. Okay. Why we are doing this? We are going to explain the effect of intensity of light that is falling. Okay, intensity of the light that is falling, which will create an impact on the photoelectric current. Secondly, how does the potential impact the photoelectric current? And thirdly, how does the frequency of the incident radiation impact a parameter called as stopping potential? So these three effects being studied with the help of this particular observation is what we call it as experimental study of photoelectric effect. And this is a very, very, very important point. This is all about the chapter. Okay. So this is the whole concept that is there in this chapter. And it is very important that you understand this. Am I clear till this point? Right? So shall we get started? So when I talk about the experimental study, so here I have the setup which is already told you, right? Now my question is, if suppose I have the source here, listen to this here. So I have the source here and I have a cathode here. As soon as the source of light comes and falls on the cathode, and I'm trying to say that the source of light already has enough frequency. So what do I mean by enough frequency? Means it has sufficient energy to knock out the electrons from this metal plate, which is the photosensitive plate. So what will happen logically? The electrons will start getting liberated. That's what is supposed to happen, right? As soon as the light falls, the electrons are supposed to get liberated. But the question is, when something gets liberated, they start traveling in some random direction. That's what happens, right? See, for example, let's say I have a dusty particle here, and I throw something on top of it. You can see that the dust is flying out. But what will happen, it will start moving in some random direction. So imagine something like that, right? So light is falling and it has sufficient frequency. Electrons will get knocked out, no doubt in that. But what can happen is the electron that is getting knocked out will start traveling in some random direction. It would have happened if you did not use this high tension battery. But by you using it, what is actually happening is electrons are coming out of this plate, and see, the C is connected to the negative terminal. So the negative terminal will actually repel the electrons. Right? So they are going to repel the electrons, and who's supposed to collect it? The collector plate. And the collector plate, since it is connected to the positive terminal, it will be able to collect the electrons with slightly accelerated value. You're able to understand what I'm trying to say? Means accelerated value means, see, if it is naturally happening, If this was not connected to the positive terminal, what would have happened is when the electrons are trying to travel, maybe they would have got attracted or they would have not got attracted also. Because we don't know what is the energy with which the electrons are getting released. Right? So what is actually happening? You are giving some energy and that energy is getting converted to some other form. Logically, that's the reason. Right? So light energy is getting converted to some kinetic energy. And I told you something at the beginning. You first need to overcome the work function of that material that you're using. So whatever material you use here, this energy should do two things. What is it? It should overcome the work function of this material and it should give sufficient kinetic energy to these electrons to travel from C to A. Right? Though it tries to do, sometimes some electrons might not get sufficient kinetic energy to travel from C to A. To ensure that there is no loss of electrons, what you do is you take the anode and connect it to the positive terminal, that is a collector plate, so that all the electrons that are getting released will try to get collected at the collector. Are you able to understand the logic behind this experimental setup? Right? So this is what happens. Right? Now, since I explained the whole story already, let me read out the points from here so that you will understand. So what they're trying to say is, this is the experimental study of photoelectric effect. So what does it mean? It is an extensive study of photoelectric effect, which was made by Leonard and R.M. Millikan. Okay. And what does this experimental setup show? It shows the experimental arrangements used in the study of photoelectric effect. What does it consist? It consists of an evacuated glass or quartz tube, which encloses a photosensitive plate C and another metal plate AA. And a quartz window W is sealed on the glass, which permits the ultraviolet light to get past and to make fall on the point C. Is that clear? So when this happens, what will happen is, this is the first thing that will happen. Electrons are emitted by the cathode and collected by the plate A called anode, or you can also call it as a collector plate. Right? And how are these two electrodes connected? These two electrodes are connected to a high tension battery, a potential divider arrangement, and a micro ammeter. Right? So the electrode C is connected to the midpoint of the potential divider arrangement, while the electrode A can be positive or negative potential as desired with respect to plate C. This is a very, very important point. Make a note of it. Right? So the electrode C is connected to the midpoint of the potential divider arrangement, while the electrode A, what is that electrode A? It is the collector plate. The collector plate can either be positive or negative with respect to whom? With respect to the collector plate, depending on the situation, which we will see in one of the experimental studies. Right? Shall I proceed? So, why do we use voltmeters? To measure the potential difference that is applied between the two electrodes. Okay. Because all these values are taken into consideration for us to draw the required graphs. Next is, when monochromatic radiations, monochromatic means radiations which have single wavelength associated with them. They have only one color associated with them. When monochromatic radiations of suitable frequency, means sufficient energy, are made to fall on plate C, electrons are emitted which are collected by the plate A. Okay, which are collected by the plate A. So when this happens, right, when there is a transmission taking place from one plate to another, what happens? Current is constituted. What is constituted? Current is constituted. So a current which has a name called as photoelectric current starts getting generated, which flows in the outer circuit, which is measured by the microammeter that you saw in the diagram. Is it clear? Right. Now, comes an important question. There. What is the difference? So I told you we study the experimental. You asked for. Did you write it? Are you done? Okay. So as I told you, we are studying the experimental study of photoelectric effect to do three analysis. What is it? One is to check the effect of intensity of the photoelectric current. Second is to check how the potential is creating an impact on what? On photoelectric current. And thirdly, you're going to check how does the frequency affect the parameter called as stopping potential, of which we are seeing the first one. So what I'm trying to say is effect of intensity of light on photoelectric current. So this is the topic. Okay, listen to this very carefully. First, see, I need to explain what exactly intensity means. Right. So you have this torch light, you're able to see. Right. So when this torch light is kept near my hand, you're able to see my hand brighter. If I take it slightly away, my hand is it is brighter, but not to the previous extent. Am I right? So here it is brighter, here it is not. So what exactly does intensity mean? So intensity has something to do with the brightness. So when you talk about the intensity of light, it speaks something about the brightness because that is a parameter that gets created. Okay. Now, if I have to give you a definition of intensity, it is defined like this. So intensity is it is the amount of power radiated per unit area. So it is the amount of power radiated per unit area. So P divided by A is going to give us the intensity. Okay. So this is not there in textbook, so make a note of it. So amount of power radiated per unit area is what is called as intensity. And its unit is going to be watt per meter square, or it is going to be joule per meter square per second. Both are same. Right, because watt is joule per meter. Sorry, watt is joule per second. Amount of energy per unit time. So joule per second per meter square. Are you able to understand this? Now, connect all these dots and try to visualize. So whenever you talk about the effect of one parameter on photoelectric current, okay, so we generally observe there are three important parameters associated. One is intensity. Listen to this very carefully. One is intensity, second is potential difference, and the third is frequency. What are they? Intensity, potential difference, and frequency. These are the three parameters which can impact a parameter called as photoelectric current. So what are they? Intensity, potential difference, and frequency. Right? So when you're trying to study the effect of one of the parameters on photoelectric effect, the other two parameters are kept constant. So this is the first technique to be kept in your mind. So here, what are we doing? We are trying to study the effect on the photoelectric current when intensity is being changed, but what are you keeping constant? The potential difference and frequency. So what do I mean by potential difference being kept constant? You remember the high tension battery? So the potential across the high tension battery is fixed. And what about the frequency? Means you are not changing the color. If you are using white light or red light, for instance, okay, if you are using a red light, you need to use only red light. You should not change. So while doing the experiment, when you are moving it closer, you should not red. When you are moving it away, you should not use nothing of that sort. Okay, it is then you can do this experimental study. Listen to this. If we allow radiations of fixed frequency to fall on plate P, okay, to fall on the plate P. So here plate P is actually plate C only, because that is the emitter plate, photosensitive plate, right? And the accelerating potential difference between the two electrodes is kept fixed. That's what I told you, right? It's kept fixed. Then one important thing that you can observe is, as you change the intensity, as you keep increasing the intensity, it is observed that photoelectric current also increases in accordance with it in a linear path. Means it is directly proportional. So listen to this point very carefully. So if you take the photoelectric current, which is a dependent quantity on the y-axis, and what is the independent quantity? What is changed? Intensity is under our control. Means if you visualize it, if you look at my hand, if there is a photosensitive plate, when you try to bring the light closer to my hand, it is observed that more number of electrons got ejected out as compared to when you move it away. Are you able to understand? Because what is photoelectric current? It is the number of electrons emitted per unit second. Right? So photoelectric current, what is happening? It will vary directly in proportion with intensity in a linear path. Means the graph will be a straight line. But here comes an important question. So when I say graph is a straight line, it is always not necessary that it has to start only from origin. It could have started from here also. Are you able to visualize what I'm trying to say? The graph could have started from here also. But it is starting from origin because I told you when we were reading the experimental study, I told you one important point. As long as the radiation was not falling on the plate, photoelectric effect was not observed. Means when light is not falling on a plate, what can I say the intensity of light is? When nothing is falling, so I didn't switch on the light. Nothing is falling on my hand with respect to this. So what is the intensity on my hand from this one? See, you are able to see my hand, brightness is there. That is because of the lights that are there around me. But I'm trying to do the experiment with respect to this light. So since this light is not falling on my hand, what is going to be the intensity? 0. When intensity 0 means there is no light incident on the surface. When no light is incident, photoelectric effect is or photoelectric current is 0. That is why you should always remember that the graph always starts from the origin. You should not start from some other point. Is this point getting registered in your mind? Right? So, since the photoelectric current is directly proportional to the number of photoelectrons emitted per second. Why did they say that number of photoelectrons per second? Because if I take the number of photoelectrons to be n and charge of each electron to be e, n into e divided by s. So, what is n into e? It is Q, quantization of charge, divided by time. So, charge per unit time is current. So that is why they told number of photoelectrons emitted per second is what is called as the photoelectric current. Okay. And this implies that the number of photoelectrons emitted per second is directly proportional to whom? To the intensity of the incident radiation. So the graph for photoelectric current versus intensity is going to be something like this. Right. So it is actually a simple concept. You need to visualize. Right. One point I would like to ask you again, what is supposed to be kept constant when you're doing this activity? Potential difference and frequency should be fixed. Is it clear? Make a note. Those who are online, are you able to understand?
Yes,
Is there any
sir.
doubt?
Yes, sir.
Good. Okay, make a note of it. Proceed to the next one. Wait 1 minute. One minute now. So we get started. Yeah. So we go to the next topic, that is the effect of potential on photoelectric current. Right? So if you see, I told you that there are three parameters associated. What are they? Intensity, potential difference and the frequency, right? So here, what are we trying to do? We are seeing the variation of photoelectric current when there is a change in the potential difference. So what are the other two parameters supposed to be kept constant? You need to keep the intensity and the frequency. Means you're going to use the same light, right? So when you say frequency is constant, same color, but this time we are going to keep the intensity also constant. Okay. So when you do this, now what I'm trying to say here is, listen. So if this is the photosensitive plate, right? I'm going to keep the intensity constant. In the previous case, what did we do? We kept moving the light, but this time what will happen is this light will be kept fixed. You're not going to move it anywhere. Okay. And let me call this intensity that is falling on this plate is I1. Now, what is going to happen when this intensity is fixed? There are certain amount of photoelectrons that are going to get ejected from the metal surface. Right. When that is happening, remember that C is connected to the negative terminal and A is connected to the positive terminal with the help of potential divider. Right. So, how is C connected? C is always connected to the negative terminal, but A with the help of potential divider can either be positive or negative depending on the requirement that we have. If we start the story, when the intensity is kept constant and the frequency of the incident radiation is fixed, what is going to happen is, if you keep changing with the help of the potential divider, if you keep changing the amount of positive potential that is existing on the anode plate. So let's imagine the story, okay? So there's a plate, collector plate, and there's the emitter plate, there's a collector plate. So light is falling on this with the fixed intensity and the fixed frequency. There are certain number of photoelectrons that are coming out. Now, when will this collector plate be able to pull those electrons? Only when it is positive, right? So if I keep it positive to a certain extent, let's say 5 electrons are coming out, for instance, let's say 5 electrons are coming out. If I keep it positive at a certain value, maybe it is able to pull only 3 electrons out of those 5 electrons. But what do I want? If I want to increase the efficiency, I'll ensure that all the 5 electrons are being pulled. So if I need to pull those electrons, what do I need to do? I need to increase the amount of positive potential on the anode. So that is why if you see, this activity is completely based on changing the potential of the anode. I never use the word potential difference. Effect of potential on photoelectric current. Whose potential? It is the potential of the anode, not even the cathode. So cathode potential is also fixed. So when you keep changing the potential of the anode, when you keep increasing it, logically think what will happen. The number of photoelectrons that are getting emitted will go and fall on the collector plate. When that happens, the circuit is completed. So when the circuit is completed, what can I say? I can say more amount of photoelectric current. Are you able to understand? That is why in this case, we will be trying to see what will happen when you increase the potential of anode in a positive way, and what will happen when you increase the potential of anode in a negative way also. I'll come to that. Now we are discussing only about the positive. Listen to this. So when the collector plate's potential is given a positive value, what I'm doing is forget about these 3 graphs at a time. So take only the first graph into consideration. Right? When you take the first graph into consideration, it is looking something like this. Right? Now, listen. Initially, when you have at the origin, the anode potential is 0. But what is not 0? It is the intensity that is not 0. So, what did we recollect from the previous activity? We told that as long as the intensity is not going to be 0, photoelectric current is not 0. That is why, if you see this graph, it didn't start from origin. So, forget about this part. On the right hand side, the graph didn't start from origin because when I had some light intensity I1 present on it, the I1 ensured that the photoelectric current was not 0 initially. Are you able to understand what I'm trying to say? So when it is not 0, as you keep increasing the anode potential in a positive way, the photoelectric current will also increase But unlike the previous scenario, it will not increase linearly, it will increase slightly in a curved manner. And after a certain point, listen to this, after a certain point, whatever value you try to increase the anode potential to, the photoelectric current will get stabilized. Means it will get saturated. So that is why the graph is in this way. So initially it will start from 0, the photoelectric current slightly increased. After a certain value, it got saturated. Is that point clear? Now you can ask me a question. Why are 3 graphs drawn on this? That is, when you have intensity I1, let's say intensity I1 is 2 units for instance. Now what I'm going to do is I'm going to increase the intensity from 2 units to 4 units. When I do that, I repeat it, listen to this carefully. When you increase the intensity from 2 units to 4 units, what will happen to the initial photoelectric current? Will it be increased or decreased? It will increase. Why? Because photoelectric current is directly proportional to intensity. So from I1 to I2, I1 was 2 units in our example, I2 is 4 units. Since the intensity increased, the initial photoelectric current also increased. That is why the graphs started slightly above. Even when there was 0 anode potential, the second graph started above the first graph. Now what I'm going to do is, from 4 units, I will take it to 6 units. Again, what will happen? The initial value will increase. Right? But in all the 3 scenarios, there is one thing that is going to happen. So once you keep this intensity fixed, right? So this intensity should not be changed during the time you are changing the anode potential. So the intensity should be changed only after you complete the activity once and then again restart it. Again, restarting in the sense the anode potential should start from 0. Okay. So when this happens, the graph on the right hand side will be like this. So first the photoelectric current will increase and then it will get saturated. Again, the photoelectric current will increase and then it gets saturated. That is when you apply the anode potential to be positive. Is this point clear? Right. Now listen to this, then you can write. Now what privilege I have is, with the help of potential divider, I can make the anode potential negative also. Means I can increase the anode potential in the reverse direction. Now again, listen to this carefully. Emitter plate is releasing the electrons. Who's supposed to collect it? A. Plate A is supposed to collect it. But now what are you doing with the help of potential divider? Now you are making this A plate as negative. Means you started giving the potential in the reverse direction. When you do this, will the electrons get attracted or repelled? They start getting repelled. Means the electrons already have some energy, but what are you trying to do? You have given a negative potential to the anode and you are making the electrons that are reaching get repelled. But there are certain electrons which will have sufficient energy to overcome this repulsion and still go and fall on the plate. And those electrons which are able to overcome this repulsion and fall on the plate will contribute to some amount of photoelectric current. But compared to the situation when the anode potential was 0, when you start giving the negative potential, is the photoelectric current going to decrease or increase? It will decrease logically because not all the photoelectrons will have the energy to reach the plate A by overcoming the repulsion. Now, let's say the anode potential is -1 volt, okay, or -1 unit, for instance. Now, I increase it to -2. What will happen? Then more number of electrons will start experiencing the repulsion. So again, what will happen to the photoelectric current? It will decrease. Again, from -2, I increase it to -3. Then more number of photoelectrons will start experiencing repulsion. Like this, the process will continue till a particular point where, let's say, the potential of this is -V0. At that point, what will happen is, none of the electrons that got emitted from the collector plate will be able to reach the anode. At that point, what is going to be the value of the photoelectric current? So when the electrons are not able to reach the anode, what is the photoelectric current? It is 0. Meaning, when you start applying the potential in the reverse direction, right? Photoelectric current will gradually decrease, and at one point it will become zero, and that potential of anode, that negative potential of anode for which the photoelectric current becomes zero is what is called as, it's not retarding potential, it's called stopping potential. Because it is stopping the electrons from reaching. Are you able to understand? So here, the last point that I would like to mention is stopping potential is independent of intensity. Stopping potential is independent of intensity. See, for intensity I1, I2, and I3, the value of initial photoelectric current were different. But when you try to apply the retarding potential, you can observe that all the values are leading to the same point of the stopping potential. Are you able to understand what I'm trying to say? So, stopping potential is independent of whom? It is independent of the intensity. Is that point clear? Right? So, this is all about this concept. Right? So I would like to stress on certain points. After that, I'll show you a small derivation that is there in this. Right. So I'll tell you some definitions that are associated. So I hope you understood the concept. Right. Now the question is, you need to know certain terminologies. So when you're giving the accelerating potential, when the potential on the anode plate is given in a positive way, what happens is, I told you that the current will attain a saturation value, and that maximum value of the photoelectric current is called as the saturation current. And at this stage, what will happen is, all the electrons that were emitted by the collector plate get collected at the collector plate, right? So this is what happens. And the next is, so I've already shown you the graph for variation of photoelectric current with anode potential. And in this context, I already told you what will happen if you start applying a negative value on the anode plate, right? So if you apply negative potential on A with respect to C and increase its magnitude gradually in the negative direction, then what will happen is, it is observed that the photoelectric current first decreases, and then it will rapidly become zero for a certain value of negative potential on plate. Right? And what is it? Potential called as. So the value of the retarding potential, I repeat, the value of the retarding potential at which the photoelectric current becomes zero is called cutoff or stopping potential. Right? And that stopping potential will occur for the given frequency and intensity of the incident radiation. Is it clear? Now, there is a small mathematical expression that we need to understand. Okay? We can use it in the problems. So, for a given frequency of incident radiation, photoelectrons are logically emitted with different velocities. So, when I say they are emitted with different velocities, they have different amount of kinetic energy, right? So, I repeat this point. For a given frequency of incident radiation, photoelectrons are emitted with all velocity ranging from 0 to a certain maximum value Vmax. Right. So, at the stopping potential V0, when no photoelectrons are emitted, right? What is actually happening? It is doing some work. When you give negative potential to anode, it is doing some work, and that work will get converted in some form of energy. See what is happening. At the stopping potential V0, when no photoelectrons are emitted, the work done by the stopping potential on the fastest electron, means the electron which has Vmax on the fastest electron, must be equal to its kinetic energy. That's what work energy theorem states. Right. So, listen to this question carefully. What is the material that is coming out? What is the particle that is coming out? Electron. Electron has a charge E. Right. And that E is moving across a potential difference of, or it is moving towards a potential of V0. Right. So, E into V0 will be the work done by the anode. So, E into V0 is the work done by the anode. That should be mathematically equal to whose value? That should be equal to kinetic energy. That's what we are trying to say. So, the maximum kinetic energy is given as half m into Vmax square should be equal to E into. It's a very, very, very important mathematical expression. So, if somebody asks what is the relation between maximum kinetic energy and the stopping potential, there is a relation. EV0 is equal to Kmax. Okay. And we will be using this expression at a later point. So, where you already know these parameters, where m is the mass, E is the charge of electron, and Vmax is the maximum velocity of the electron. So, all these values are taken in order respectively. Right. So, this is all about the variation of. So, this is all about the variation of photoelectric current with potential. Whose potential? Anode potential. Last chapter, we have very less actually. Last year itself, they deleted 7 years. Last year, 20% added. This chapter, nothing is cooking. It's easy actually. I think you would have already learned photoelectric, not in depth. Because we are involving a lot of physics. Yeah. So that one concept is left out with respect to the experimental study that we'll see it in the next class. So is it a holiday next week for you guys? Monday, Tuesday, Wednesday is holiday. Thursday. Thursday, Friday will have school. Monday, Tuesday, Wednesday is holiday, right? Okay. Hey, those who are online here, from it, I know about DAB. Anyone from other school, tell me. Morning will Morning will be fresh, no, we can close it. CV,
Yes, sir.
is it holiday next week? Fifth, sixth, fourth, sorry, third, fourth, fifth?
Yes, sir. Actually, fifth, I'm having my reopen night test, sir.
Fifth, I don't think you will have it. Vijayadashmi, I think most of the schools close. Check it once again.
Okay, sir.
Okay. I need an answer from Ramasubramaniam Bhagat Kumar. ஏதோ chatல போட்டிருக்காங்க. Sir, morning, I can't attend. I am having another class. Okay, ma'am.
Sir, fifth is holiday, third, fourth, I don't know, sir. They didn't
Okay.
inform.
Let me know by today. Okay. I need to
Okay,
plan
sir.
the next. So that's it. That's it for today. In my mind. When- Other voice, email. Guys, we'll wind up.